Hi, today we are building an AI agent that can autonomously find and fix bugs in your codebase, like the cursor. Instead of just exporting what's wrong, it reads files, identifies issues, applies fixes, and verifies the solution, all without human intervention. We'll use a local LLM via Ollama, function calling, and an agentic loop that lets the AI decide its next steps based on what it discovers. Our goal is an agent that takes a bug description as an input, explores the code base to understand the structure, identifies the bug, fixes it by writing correct code, tests the fix by running the code, confirms success, and stops. Let's look our schema now and what we need to build this agentic AI. We need to create the following functions. Get files info that lists files and directories in the specified path, returning each item's name, size, and whether it's a directory with a security check to ensure the path stays within the working directory. Get file content that reads the file's content from a path relative to the working directory, validates the path, stays within the working directory, and returns the content or an error if the file doesn't exist or can't be read. Code tool looks up a function by name in the current module's globals, calls it with the working directory and unpacked arguments, and returns the result or an error if the function is missing or the call fails. Parse and execute text tool call. Parse a text-based tool call from the LM response using regex, extracts the function name and arguments, executes the tool, append the result to the message array, and returns true if a tool was called or false if it's a final response. Write file writes content to a file at a path relative to the working directory, creates parent directories if needed, validates path stays within the working directory, and returns a success message or an error if writing fails. Run Python file executes a Python file in a subprocess with a 30-second timeout, validates the path is within the working directory and is a Python file, captures ctd out, ctd error, and returns the output or an error message. Get API response. Send messages and tools to the LLM API with exponential backoff address. Returns the response on success or none if the model doesn't support tools or all threads fail. Handle structured tool calls. Processes structured tool calls from the LM response. Extract functions names and arguments from each tool call. Executes them via call tool function and appends the results to the messages array with the proper tool call IDs for the next API request. Our agent needs iterations because each step depends on the results of the previous one. It must see the file list before reading files, read the code before fixing it, and verify the fix before confirming success. On the first iteration, we call getAPIResponse to send the initial prompt to the LLM. The model analyzes the request and decides to call the getFilesInfo function to explore the code base. Next, handleStructuredToolCalls function processes the tool call. It extracts the function name and arguments, executes getFilesInfo function via callTool function, and receives the result listening files. This result is appended to the messages array as a tool response, so the LLM can use it in the next iteration. The cycle continues with the updated context. On the second iteration with getAPIResponse, the LLM sees the file list from iteration 1 and decides to call getFileContent function to read a specific file. Next, handleStructuredToolCalls extracts the function name and file path, executes getFileContent function via call2 function, and receives the file content, in this case class temperature converter. This result is appended to the messages array as a toResponse, so the LLM can analyze the code in the next iteration. The cycle continues with the updated context. On the third iteration, the LLM analyzes the code from iteration 2, identifies the bug, and decides to call writeFile function to apply the fix. Next, handleStructure2 call function extracts the function name, file path as always, and corrected content, executes writeFile function via call2 function, and receives confirmation. File written successfully. This result is appended to the message array as a toResponse, so the LLM can verify the fix in the next iteration. The cycle continues with the updated context. On the fourth iteration, the LLM sees the file was written in iteration 3 and decides to call runPython function to test the fix. Next, handleStructure2 calls extracts the function name and file path again, executes runPython function via call2 function, and receives the execution output. This result again is appended to the message array as a toResponse, so the LM can verify and fix in the next iteration. The cycle continues with the updated context. And on the fifth and final iteration, the LLM sees the test output from iteration 4, confirms the bug is fixed, and returns a final response with no two calls. Next, pass and execute text2 call function processes the response, it checks the two call patterns, finds none, prints the final response, and returns false. The main loop receives false, breaks out of the while true loop, and the agent stops. The bug is fixed and verified. Let's see our message flow diagram. The conversation history is built step by step. It starts with the system prompt, which sets agents, roles, and instructions. Then we add the user request, the bug description. When the LLM decides to use a tool, we add a tool call to the history. After execution, we append the tool results. This repeats. Another tool call and its two results are added as the agent explores and fixes the code. When the task is complete, the LM returns a final response with no tool calls and the loop ends. Each iteration appends new messages to the history, so the LM has full context for its next decision. This is how the agent maintains awareness across multiple tool calls. And with that, we are finishing part 1 of our tutorial on building an agent that searches for bugs in our code and fixes them. Please follow me to part 2, coding, where we will program and test our agent. Links to download the codebase are in the description. Now, after the theoretical section in part 1 of this tutorial, let's build our agentic bug hunter AI. We will start by setting up our project structure and implementing each function we discussed. Then wire them up together into a agentic loop. First, we have to install UV. It is a modern Python package installer that's significantly faster than pip and manages dependencies and virtual environments for Python projects. Also, I'm using Llama because it lets me run LLMs locally. It exposes an OpenAI compatible API, so our code works with local models without changes. We'll use it to run models like Queen on our machine. And the first thing that I will do is creating the functions folder, and of course the function or just fn.py. Next, I will create the env file with the following content, but not here. What we have here is the LM model name for Llama Queen. After that we have the working directory converter. This is where the LM is going to work. Max chars are the maximum characters for reading from a file, because we are going to read files and fix bugs there. Max retrieve are maximum API retrieve attempts. Open API base URL. This is the Llama API endpoint URL. And the OpenAI API key is the API key that we are using. Next step is to import the necessary packages in our function file. We have import JSON. This is for JSON parsing and serialization. OS, the operating system package for OS operations like paths, environments, and etc. Regular expression for pattern matching. We need the system-specific parameters from sys package, time utilities package for timing functions and features, subprocesses. We need this to run external processes, and .env that loads variables from the env file with that function. Next, we need to write our first function called getFilesInfo. That will list files and directories in the specified path, returning each item's name, size, and whether it's a directory, with a security check to ensure the path stays within the working directory. So let's explain how this function works. The function takes working directory as a required parameter and an optional directory parameter that should be none. If directory is not provided, it's none or is an empty string. We default it to the current directory within the working directory. On the next line, we convert working directory to an absolute path. Default parameter handles omitted arguments. This line handles explicit none or empty values from the LLM. Python's OR uses short circuit evaluation. If directory is truthy, it returns the directory. If it's falsy, it returns the current directory within the working directory. OS path join joins the working directory path with the directory parameter into a single path, and OS path apps path converts that joined path to an absolute path. Next line, we are doing security check that ensures the target directory is within the working directory to prevent path reversal. Then we create the variable final response that initializes an empty string to collect the output. OS listDir function lists all items, files and directories in the target directory. And we iterate with the for loop over contents. We build the full path to each item and check if the item is a directory. After that, we get file or directory size in bytes. In the final response, we append the formatted info to the response string and return the complete listing. Next function, getFileContent. Let's explain the function how it works. The function takes two variables, working directory and file path. First, we convert the working directory to an absolute path. Then we join it with the file path and convert it that an absolute path as well. Next, we perform a security check. If the file path doesn't start with the working directory, we return an error to prevent path traversal attacks. We also verify that the path actually points to a file, not a directory. If it's not a file, we return an error. Then we try to open and read the file. We read up the maximum number of characters specified in our maxchars environment variable. If the file is longer than that limit, we truncate it and append a message indicating where it was cut off. If any error occurs during reading, we catch and return an error message. Otherwise, we return file content. Next important function that we need to build is writeFile. Very important function. So what is happening here? This function writes content to a file at a path relative to the working directory. First, we convert the working directory to an absolute path. Then we join it with the file path and convert that again to an absolute path. Next, we perform the same security check. If the file path doesn't start with the working directory, we return an error to prevent writing outside the project. We get the parent directory of the target file. If that parent directory doesn't exist, we try to create it using OS makeDirs function with existOK2 parameter, which creates all necessary parent directories. If creating the directories fails, we return an error. Then we try to open the file in write mode and write the content. If the write succeeds, we return a success message. If an error occurs during writing, we catch it and return an error message with details. Our next important function is run Python file. This function executes a Python file in a subprocess. First, we convert the working directory and file path to absolute paths. Then we perform the same security check. If the file path doesn't start with the working directory, we return an error. We verify the path points to an actual file, and we check that it ends with .py to ensure it's a Python file. And if any validation fails, we return an error. Then we use subprocess.run to execute the file. We pass sys.executable as the Python interpreter and the file path as arguments. We set the working directory as the current working directory for the subprocess, set a 30-second timeout to prevent hanging, and capture both std_out and std_error as texts. We built a response string starting with the standard output and standard error. If there is no output at all, we add a message indicating that if the process exited with a non-zero return code, we append that information. We return the complete output string. If the execution times out after 30 seconds, we catch that exception and return a timeout error. If any other error occurs, we catch it and return an error message. Our next function is callTool. This function looks up a function by name and calls it with the provided arguments: function name, function arg, working directory, and verbose. We use globals.get to retrieve the function from the current module's global namespace. If the function doesn't exist, we return an error message. Otherwise, we try to call the function passing the working directory as the first argument and unpacking the remaining arguments using asterisks. If a type error occurs, it usually means required arguments are missing, so we return a specific error message about that. If any other exception occurs during execution, we catch it and return the error message. This allows the agent to dynamically call any of our two function names. Our next function is getAPIResponse. This function wraps a chat completion API call with retry logic and error handling. It makes the API call resilient to temporary failures and handles model compatibility issues. We define getAPIResponse with 4 parameters: client, the API client, messages, the conversation history, tools, function definitions for tool calling, and max retries, defaults up to 5. We use a for loop that runs up to max retries times, giving us multiple attempts if the API call fails. Inside the loop, we wrap the API call in a try block to catch exceptions. We call client chat completion create with 3 arguments: model from the environment variable, messages, the conversation history, And tools, function definitions. On success, we return the response immediately. If an exception occurs, we convert it to a string to inspect the error message. We check if the error indicates the model doesn't support tools or function calling. If so, we print an error message and return none immediately. No letters for this type of error. For the other errors, we check if we have letter remainings. If yes, we calculate the wait time using exponential backoff, 2 to the power of the attempt number, giving us 1 second, 2 seconds, 4 seconds, and 8 seconds, and so on. This prevents overwhelming the API with rapid letters. We print a message showing the wait time and current attempt number. Then we call timesleep to wait before the next attempt. If all letters are exhausted, we print an error message with exception details and return none. If the loop completes without a successful return, we return none as a final fallback. Our next function is parse and execute text to call. This function passes text-based to calls from the model's response, executes them, and updates the conversation history. It's used when the model outputs to calls as plain text instead of as structured format. We define this function with 4 parameters: content, the model's text response, messages, the conversation history, working directory, where file operations happens, and verbose, optional flag for detailed output, defaults to false. First, we strip white space from the content using strip to clean up the input. We use a regex pattern to search for to-call syntax in the text. The pattern looks for a JSON-like structure containing a name field, the function name, and arguments field, the function parameters. This regex extracts both the function name and its arguments as separate groups. If a match is found, we proceed with executing the to call. We extract the function name from the first capture group of our regex match. We attempt to parse the argument string as JSON. If parsing fails, for example invalid JSON, we catch the JSON decode error and defaults to an empty dictionary, preventing the function from crashing on malformed arguments. We print a message indicating which function is being called. If verbose mode is enabled, we print the function arguments for debugging purposes. We call call-to function with the extracted function name, passed arguments, working directory, and verbose flag. This actually executes the function. If the verbose mode is enabled, here, this piece of code, we print the result, print. If the result is longer than 200 characters, we truncate it and add an ellipsis to keep the output manageable. We append the two messages to the conversation history. 1, 2. First, we add the assistance message containing the original content, the tool call text. Then, we add a user message containing the tool result and a reminder to respond in English. Return true to indicate that the tool call was found and executed. If no tool call pattern was found in the content, we print final response, followed by the content itself, treating it as the model's final answer. We return false to indicate no tool was called. Our next function is handle structured tool calls. This function handles structured tool calls from models that support native tool calling format. Unlike the text-based parser, this works with properly formatted tool call objects from the API response. We define handle structured tool calls with 4 parameters. Message, the assistance message object containing structured tool calls. Messages, our conversation history, working directory, where file operations happen, and verbose, optional flag for detailed output, defaults to false. First, we append the assistance message to the conversation history. This preserves the model's response with its tool call request. We loop through each tool call in message tool calls. The model can request multiple function calls in a single response, so we process them one by one. For each tool call, we extract the function name from toolcall.function.name. This is the name of the function the model wants to execute. We pass the argument string as a JSON using JSON load. The argument came as a JSON string, so we convert it to a Python dictionary for use in the function call. We print a message indicating which function is being called. If verbose mode is enabled, we print the function arguments for debugging purposes. We call callTool function with extracted function name, passed arguments, working directory, and verbose flag. This executes the actual function. If verbose mode is enabled, we print the results. If the results exceeds 200 characters, we truncate it and keep the output readable. We append a tool message to the conversation history. This message has the role tool include the tool call ID to link it to the original request, and contains the result as a string. This tells the model what happened when the function was executed. We append a user message with a reminder to respond in English only. This ensures the model continues the conversation in the correct language. This function doesn't return a value, it modifies the message list in place, updates the conversation history with all tool call results. Next, we have to create a new function or a new file called prompt.py, and here we have to insert our new function getSystemPrompt. This function centralizes the agent's instructions, making it easier to modify the agent's behavior by changing the prompt template. The working directory is injected dynamically, so the same prompt works for different project locations. The function returns an F string containing the complete system prompt. The F string allows us to inject the working directory into a prompt dynamically. The prompt starts by defining the agent's role. You are an AI coding agent. Your job is to fix bugs, not explaining them. This sets the expectation that the agent should take action, not just describe problems. There is a strict language rule. English only. The prompt emphasizes that all responses must be in English, with no exceptions. This prevents the model from switching to other languages. Next, we have Critical Rules section with 5 rules. Don't explain. Use write file to actually fix the code. Rule number 1. Rule number 2. When writing files, include the complete file content, all functions and methods. Don't truncate or simplify code. Copy the entire file and only change the buggy line. Rule number 3. And rule number 4. Never give a final response until the code is fixed and tested successfully. And rule number 5. Stop immediately after the test passes. When run Python file function shows correct output, give a final response and stop. In the last video, we explored the getSystem prompt function, which centralizes the agent's instructions and dynamically injects the working directory. We defined the agent's role, enforced the English-only rule, because we are using a Chinese model and we often translate into Chinese. And we went through the 5 critical rules that guide the agent's behavior. This is where we stopped in our previous video. We've set up all the rules, but we haven't discussed exactly how those rules control the agent's workflow in practice. In this video, we will continue by showing how these rules prevent the agent from explaining instead of fixing code, ensure complete file rewriting, and stop the agent once the bug is fixed. We will also walk through the working step by step from reading files, applying fixes, running tests, to confirming success. By the end, you will see how these prompts ensures the agent taking fully verified deterministic actions. If you are enjoying these coding tutorials, consider liking this video and subscribing to the channel. It really helps us keep making free, high-quality content for developers like you. Thank you. These rules prevent the model from explaining instead of fixing, writing incomplete code that breaks files, or continuing to modify code after the fix already works, ensuring the agent takes complete, verified actions and stop when done. Next section is workflow. The prompt provides step-by-step guidance. Use getFileInfo function to list a file. Use getFileContent to read the file and the entire buggy file. Use writeFile to write the entire file with the fix. Use runPythonFile function to test. Expected output is 0 Celsius or 32 Fahrenheit. If the test shows 32 Fahrenheit, the bug is fixed. Give a final response and stop. At the end, we have a bug description in case, and we can create this description dynamically, but for now it is hard-coded. The function incorrectly multiplies Celsius by 2. but it should use the correct conversation formula, multiply by 9, divided by 5, and add 32. The prompt includes instructions for what to do if the test fails. Read the file again and try again. If the test passes, stop immediately and don't modify anything else. At the end, the prompt includes the working directory path using f-string formatting. All paths are relative to the working directory. This tells the agent where to operate. Okay, so our next phase is to create a temperature converter application that converts Celsius, Fahrenheit, and Kelvin with direct conversions for adjacent scales and indirect conversions for non-adjacent pairs. We need to create our folder called converter. And inside our converter, we can create our file called temperature.py. And this is the temperature converter class that provides temperature converter methods. Our first method, Celsius to Fahrenheit, takes a Celsius value and returns a Fahrenheit using the formula multiply by 9, divided by 5, and add 32. Next method, Fahrenheit to Celsius, takes a Fahrenheit value and returns a Celsius. The Celsius to Kelvin method here converts Celsius to Kelvin. Kelvin to Celsius, it's opposite, converts Kelvin to Celsius. Fahrenheit to Kelvin method converts Fahrenheit to Kelvin with those calculations, and Kelvin to Fahrenheit method of this class converts Kelvin to Fahrenheit. And that's for this class. Okay, so after we build the functions, the agent for manipulating the code and creating our temperature converter app, it's time to test and see the results. I've already tested and everything worked perfectly, but here I can test it again so you can see it too. First, we have to break a line. For example, we can say, and we can make that kind of mistake, and then we can run the code. Am I missing something? Well, I don't think. Well, we will see. Now, this is the command that I'm running, UV, because we use that, the main py, and this is our message that something is not working properly. And enter. Has been created. Do you want to select it for the folder? Yes. So probably we are missing something in main. Let me check. Oopsie, it looks like I forgot the logic that works with the LLM and our temperature app. Something that I have to write here in the main.py file. So let's start doing that. So let's put the code. And what we have here, this is the main point of our agentic AI system. It orchestrates the conversation with the AI model, handles tool calls, and manages conversation loop. We import OS and sys for system operations. load.env to load environment variables, our helper function from functions.fn, the OpenAI client, the system prompt generator, and the tool's definition. We configure standard output to use UTF encoding to properly handle special characters and emojis in the output. We call load.env to load environment variables from env file, which contains API keys and configurations. Actually, here we are loading. And we are defining the main function that contains our core logic. Next, we create an OpenAI client instance using the base URL and API key from environment variables. This allows us to use different API providers by changing the base URL. Check if at least one command line argument was provided. If not, we print usage instructions and exit. Check if the verbose flag is present in the command line arguments to enable detailed output. We extract the user's prompt from the first command line argument. Next, create the initial messages list with two messages. A system message containing our system prompt generated with the working directory, and a user message with the prompt and a reminder to respond in English only. I do that often because I'm using a local Chinese model, LLM, and very often responds in Chinese. We enter an infinite while true loop that continues until the agent provides a final response. Inside we call getAPIResponse with the client, messages, tools, and max address from environment variables. If the response is none, we return and exit. After that, extract the message object from the first choice in the API response. If the message contains two calls, we call handle structure two calls to process them, execute the functions, and update the conversation history. If the message has content but no structure to calls, we try parse and execute text to call to check for text-based to call patterns. If it returns false, meaning no to call was found, we break out of the loop. Break. Else, if the message has neither to calls or content, we print an empty final response message and break again. If verbose mode is enabled and the response includes usage information, we print the prompt token and completion token used, which helps track API cost. We use the ifMain guard function. That function only runs when the script is executed directly, not when imported as a module, because we can import that as a module. Okay, so ready to test again? We should run our command again and see if we're missing another code or piece of code or something, but probably should work this time. And we are missing something. Let me check. Okay, so this error is coming from missing dependencies that I have here and I have to fix. Pilot.gmb, OpenAI. So let's see now. Now it works, I think. Going to temperature and looking. Okay, so we hit another problem. Let me check that one again. I think this one is just a missing letter here because it requires prompts. We have only prompt and probably right now should work. Let's test again and we are looking this and tools. Functions, prompts. Let me check that again. And yep, tools is missing. Tools file where we have to put our tools. Now we are creating this file tools.py and this is our function that I have to explain now. DevTools. This function it defines the function calling schema that tells the AI model which functions it can use. It takes a name, description, and params and return a dictionary matching the OpenAI function calling format. We create a tools list with 4 tool definitions. Get files info for listing files, get file content for reading files, write file for writing files, and run Python file for executing Python files. This list is important in main.py and passed to the API, enabling the model to call these functions during the conversation. And let's check now to see if it is working. It should work. It's taking a little time. It is taking time. Yep. Right now should we go to the calling function get file info. It looks like it's working. It's doing the work at the moment. But Python is a little bit slow compared to many other languages. Write file. And I think it fixes the bug. It fixed the bug we were having. Yep, it worked this time. And yeah, this is because of I'm using a Chinese LLM and yeah, I'm getting those kind of responses all the time. But it did fix the bug and it is working properly. That is the final goal at the moment. Also, I want to make one more test. prompts. I want to remove this. Go to the ban. That shouldn't be here. And let's break it again. Something like that, for example. And see. And we have to wait again because it's taking time. For now I didn't focus on the architecture of the project, improving star or any kind of security or anything at the moment. I'm focusing only on the building the agent that is fixing bugs inside your code. Okay, get files info. Get file content. I forgot to mention that the link to the code is in the description down below in the video. You can go to the GitHub, download it and check if you're missing something or you're forgetting something. So the link is down in the description. And we are waiting for the next step. Sorry that it's taking that much time, but as you can see, it fixes the function again as before, and we remove this additional prompt that I used in the beginning to help me a little bit to speed up the process. But right now it's working properly without any issues, without any problems, and it is providing everything in English. At the moment works really very well, fixes bugs, fixes everything. Thank you for watching, and please like and subscribe the video if you find any value for yourself, and if you learn something, it will help me boost the channel a little bit. Thank you.